Welcome, everybody. This is Christian Schmitz from PDIE Group, Purpose Driven Innovation Ecosystem. Today, we have a very interesting guest and a very interesting discussion with Professor Dr. Bärbel Hönisch. She is sitting in New York right now, and it's morning time in New York, and it's late evening here in Tokyo. So welcome, Bärbel. And please give us a little bit of background about yourself and tell us how you got into the topic of Paleo CO2 and how you got to the Lamont-Doherty Earth Observatory, where you are researching and probably also teaching. So thanks for being with us, and looking forward for a very interesting conversation with you.
Thank you. So I was originally trained as a biologist, and before I studied biology, I actually wanted to restore paintings, and that did not work out. And so at some point, I flipped through an encyclopedia, and I found a list of the Max Planck Institutes in Germany, and there was one about marine microbiology. And I skipped the micro, and I thought marine biology sounds great. And I saw dolphins and whales in my future. And so I wanted to study marine biology. And so I studied in Germany, and I went to the University of Bremen and learned very, very quickly that there are very few biologists who actually happen to work on marine mammals. And that most of the work that is done is really on biological oceanography, meaning that we're working on plankton organisms. And so there was one part. The other part is that Bremen has a very strong geology department, and I was very intrigued by that. So they have they take very many sediment cores in the Atlantic Ocean, and so I actually ended up doing my diploma thesis at the University of Bremen in the geology department, and I worked on ear stones of fishes and reconstructed climate change from that. So that was quite exciting. And then afterwards, I did a PhD at the Wiener Institute for Polar and Marine Research in the carbon group. And in that group specifically, I worked on planktic foraminifera. And planktic foraminifera are unicellular organisms. They are plankton. They float in the ocean, and they secrete a calcium carbonate shell that looks a little bit like popcorn, but is essentially equivalent to what a snail, for instance, makes. And so in these shells, it incorporates the chemistry of the water when it's living. And so I was very intrigued by that. And I was particularly intrigued by a new method that allowed us to reconstruct seawater acidity from boron isotopes in these shells. And I learned from a very, very smart young Indian man who came to Germany and who taught me how to do these analyses in Kiel. And the first time we analyzed the sample and we opened the valve so that we got a signal. He called me the queen of boron, and I was hooked. So he was a very, very nice man, a very, very kind man, and a very good mentor. And so afterwards, I contacted his PhD advisor, who was Gary Hemming, and he worked at the Lamont-Doherty Earth Observatory at Columbia. And I sent him a message with a manuscript that I had written at that time. We said, "Oh, that's very interesting." And then I didn't hear from him. And half a year later, he asked me if I wanted to do a postdoc with him. And so I was very intrigued by that, because the institute that he had done his analyses in was in Stony Brook on Long Island. And there was an instrument that was originally built to analyze the moon samples. And that seemed to be the only instrument that anybody could reasonably measure boron on. And so I wanted to go there. And yes, he asked me to come. And so, of course, I said yes. It was for 1 year, that original position. And here I am 21 years later.
21 years. That's a long time. So you have been, and is it actually in New York, or Columbia University is in New York, but the Earth Observatory?
The Lamont is a little bit outside of New York. It's about 16 miles from here. And it's a campus that was originally donated to Columbia. And it was very useful for the seismology department because of all the subways that were being built here, and they couldn't measure the vibrations of the ground anymore without measuring the vibrations of the subways. And so that's why we have a campus that is outside of the city. But so my laboratory is there and my office is there, but I teach at the university in the city.
Great. And what kind of courses are you actually teaching?
Right now, I'm teaching a course on Introduction to Oceanography for non-science majors. I also teach a course on global warming, and I teach a course on Cenozoic paleoceanography. The Cenozoic is the last 65 million years. And so we're looking into what we know about the environment at that time, and in particular from the ocean's perspective.
And this is what I have been so fascinated about when just a couple of days ago, I was reading an article in Spiegel Online where your name was mentioned on the very top of this article. And this article was actually about global warming, the causes of global warming. One of the causes of global warming is CO2, which is one of the greenhouse gases. And this article was describing this group of 80 scientists, which you are somehow supervising, which are all around the world, and they have different methodologies, and they would contribute to getting insights about the concentration of CO2 millions of years ago. And when everybody in their childhood, everybody who is a child will come across the dinosaurs, and we call this, I don't know if that was the first mass extinction or but this was really fascinating. So I would like to ask you, first of all, to explain a little bit to people who are a little bit skeptical or new about this topic, climate change. What is main causes for climate change? We know it's a systemic issue as well, but these greenhouse gases and especially CO2 play an important role in this. So I would like you to highlight a little bit the role of CO2 and these greenhouse gases. And then we go a little bit back in the Earth's history and examine a little bit how it actually came together.
So first of all, greenhouse gases are very important. If we didn't have greenhouse gases on our planet would be frozen, and so there would be no life on our planet. So having some greenhouse effect is a very important thing. And a lot of that greenhouse effect actually comes from water vapor, but there are additional gases like carbon dioxide and methane and many others. And what these gases do is that they allow the radiation that's coming from the sun to come on the ground. They allow that to come in almost unfiltered. Not entirely. There's some gases that take out UV radiation and other things. But once that radiation interacts with the surface of the Earth, it heats the surface of the Earth, and it gets re-emitted in the form of somewhat longer range, longer wavelength radiation. And these longer wavelengths that Earth emits, they can then interact with some gases in the atmosphere. And as I mentioned, water vapor is one of them, carbon dioxide, methane. And so what happens is that longer wavelength radiation that will then actually be re-emitted back to the surface of the Earth. So the more of these greenhouse gases we have, the warmer we will make our planet. And that is something that we have observed in Earth history. So our Earth, for instance, has had very, very high carbon dioxide concentrations in its youth, and the carbon dioxide concentrations have decreased over time. Right now, we see that the carbon dioxide concentrations are increasing because of human activities, because of fossil fuel burning and concrete production and land use changes. We're cutting down forests and other things. And so that increases both the carbon dioxide concentration and also the methane concentration significantly. So what we know from actual measurements in the atmosphere that started in 1958 on Mauna Loa, on a volcano on Hawaii, is that At that time, the carbon dioxide concentrations in the atmosphere were on the order of 318 parts per million. So just look at the numbers. Don't worry about the parts per millions of ppms. That's just the unit that we're measuring. And over time, we have now reached 420 parts per million. So the carbon dioxide are increasing significantly. Excuse me.
Yeah, so I think there's this magical threshold of 350 ppm, and there's also an organization, an NGO, calling themselves 350.org. They are activists, and now we have already surpassed these 350. Maybe you could highlight a little bit. You said in the use of Earth, we had the highest concentration of CO2. How is that comparable, for example? And how could we imagine the climate in these conditions?
Oh, so this is something that happened billions of years ago, and we don't really know what exactly the carbon dioxide concentrations were. They must have been much, much higher than today, because there was a lot of volcanism that produced a lot of carbon dioxide. There were no trees, no plants on land that actually sequestered carbon dioxide and turned it into fossil fuels. So this was a very, very long time ago. We would love to hear or learn a lot more about how Earth has evolved and the carbon dioxide in the atmosphere has evolved since the explosion of life on our planet. So this is actually a project that we're working on now as a follow-up project of the one that we started earlier, that is to compile data that go back to about 600 million years ago. We actually really only have data back to 470 million years ago. But they're very scattered, and so we want to work on that in more detail. So what happened since then is that is somewhere around 470 million years ago, trees evolved. So we had plants on land that consumed a lot of carbon dioxide. They built our coal. There were coal swamps that developed at that time. So they developed our coal deposits. Over time, we had a lot of carbon dioxide sequestered into marine deposits as well, and so those are the oil and gas reserves. So that has drawn down a lot of carbon dioxide. But carbon dioxide has gone up and down over Earth history repeatedly. That is also related to how the continents are moving and whether we're making new ocean basins where the continents are moving apart. That leads to a lot of volcanism between the new continents. And then there are times when the weathering of rocks on land, when we have newly exposed rocks, for instance, like the Himalayas that were exposed about 50 million years ago, they also sequester carbon dioxide, or the weathering of those rocks with the help of carbon dioxide in the atmosphere and water that actually neutralizes carbon dioxide. And so that is probably the reason why over the last 50 million years or so, the carbon dioxide has actually decreased quite substantially. And we're now actually in a period of Earth history where carbon dioxide is almost lower than it has been ever before. So that's a very interesting parameter in this equation, because we're always talking carbon dioxide is going up, so we need to be concerned about that. But right now we are actually at a very low concentration of carbon dioxide in Earth history.
That's really interesting, and it might encourage the skeptics about climate change to say, yeah, then maybe there's nothing to worry about. So how could we put that a little bit more into context? I mean, during the Earth's history, we also had times like the Ice Age, where the planet was cooling down a lot. And now we call it the Anthropocene, which means that human activity has actually caused. And you mentioned these coal swamps, and the plants which sequestered carbon millions and millions of years ago, and that nowadays, or since the last 150 years, some human beings discovered oil as a very good carrier for energy with a high energy density, and which would be cheap, and then we would just burn it and it would go into the atmosphere. And we have done it now more than 150 years. So nevertheless, you just said that we are actually at a very low concentration. So how can we put this into context so that we can see that nowadays, even these days, COP28 in Dubai is happening. The countries are negotiating, and people talk about the 1.5 degrees and the tipping points. So I just wanted to hear a little bit your context about this.
I think first of all, we have to realize that Earth does not care about us. It does not care about what the climate. Earth will survive us and whatever we're doing. So because it has seen much more significant changes in the past, that is absolutely correct. Now let's put these numbers into perspective. So I have mentioned 420 parts per million today, 316 or so when we first started measuring carbon dioxide in the atmosphere. There are ways of going back in time, and the most important one is actually the ice cores. So when snow is falling on Antarctica, at some point that snow compacts so much that it turns into ice. That takes a long time, about 80 years, until there's enough snow that finally makes it dense enough to form ice. In that ice, we have bubbles of ancient air enclosed. So at the time when that goes from snow to ice, these bubbles get enclosed in that. And scientists can actually measure the composition of these bubbles. And that's the gold standard of paleoclimate research, because it's an actual archive of old air. From those times, from those ice ages, or from the ice cores, we currently have a record that goes back 800,000 years. And in these 800,000 years of ice core records, we have seen that carbon dioxide went up and down about every 100,000 years. And it fluctuated between 280 parts per million during warm times, and 180 parts per million during the ice ages. So that's 800,000 years carbon dioxide fluctuating between 180 and 280 parts per million. Now, as you mentioned, over the last 150 years or so, since the Industrial Revolution, we have increased carbon dioxide to 420 parts per million. So that's much, much higher compared to what we have seen in a long time in Earth history. Now, humans have been around, or let's say our genus Homo has been around for 3 million years. So that was a time when, during the Pliocene, when we did not have any ice on Greenland. Greenland really only started glaciating about 2.7 million years ago. So the climate was very different at that time. And then over these last 3 million years, we have been in a time with relatively low carbon dioxide concentrations that were, from what we know now, lower than what we have what we see today. So that means that people have evolved in a cool climate, even though there have been times in Earth history that were much, much higher concentrated in carbon dioxide and much warmer. Humans have evolved in a cool climate, and we have built our civilizations and all our infrastructure in these environments that see the sea level as it is today. We see now we have temperate regions where we receive a lot of rainfall. There's ice on the poles. The tropics are warm. So all of these conditions that we're seeing today, they have existed for the last couple million years. There were significant changes, in particular with the ice ages. During the ice ages, sea level was 125 meters lower compared to today. So that's quite substantial, because we had all that water from the ocean was actually deposited as snow and ice on Antarctica and Greenland. But so these are quite substantial changes in the climate. But it is really important for us to realize that we have evolved in this cool climate, and that is what we are adapted to. So when the skeptical reader comes and says, well, so we look back 50 million years, 60 million years ago, and we see carbon dioxide levels were much, much higher than today, why do we care? We care because at that time it was globally almost twice as warm as today.
And
so that's
it would have been inhabitable for humans or for any other mammal species?
No, we did have mammals. So the at the end Cretaceous, when the dinosaurs got wiped out by that meteorite impact, there were small mammals around. They were kind of on the size of a mouse or maybe a small cat. And since then, the mammals have evolved. And so they have evolved over many of these time periods when it was actually very, very warm. But those organisms or those animals actually also evolved at a time where they didn't know any difference. They have since gone extinct because of new evolution of new organisms that have come around, but they evolved in a very different climate, and it was habitable in some places. So if you go to the tropics, we had alligators in Greenland and Antarctica. So many of these tropical species actually lived at much higher latitudes. So they would have gone to the cooler parts of the planet, and those were perfectly fine to live in. And that is maybe also the comparison that we can draw today. Those of us who have enough funds, we can move out of the way. We can move away if our house gets washed away. We have insurance that pays for that house, and we can install an air conditioning unit if we think it's getting too hot in the summer. But many people do not have that option, and so of course that now brings it back to migrations, to political conditions that will become very, very difficult if all of a sudden a lot of people start migrating because some places on the planet are not habitable anymore. And so that's where
now this is a very good transition, actually, like talking about the consequences of global warming and exponential heating of certain areas, especially the south, the global south. They call it now the global south. And we had this event in New York, the Future of Climate Summit, where we had invited this activist, Hindu Umaru Ibrahim. She's from Chad, and Chad is in this sub-Sahel region, and it's very dry, and it's getting hotter and hotter, and it's becoming more and more difficult to actually have agriculture and make meaningful use of the land. So what do you think? On the one hand, we have the consequences, like migration is something which becomes a big risk factor. Also, we can see more and more people flooding into Europe, for example, and also in the US, coming from the south. And so on the one hand side, the consequences, and then to close this a little bit, going towards a conclusion, what we can actually do, that would be a great way to come to a conclusion of this short conversation.
Well, the consequences, we're seeing a lot of these consequences already. So the climate models predict that wet places will get wetter, dry places will get drier. We see people from dry places moving away. So if you don't have water, you can't grow crops. You don't have water to drink. So water is really the most important aspect that we have on our planet. Without water, we don't have any life. And the lack of water is actually the main reason for conflicts and wars in the world. So that is a really important aspect. And so in particular, the dry places getting drier is very disconcerting. We have seen a lot of wildfires in particular in the Western US because of the drought conditions that are increasing there. At the same time, when we do have storms, and when we so many of these storms are becoming more violent, they carry a lot more water when that is happening. So when you dump a lot of water on very dry soil, that means that the soil cannot take up that water, and so that's when you end up with flash floods. So when you end up with serious flooding, that causes a lot of damage to the infrastructure as well. And then storms in general. So just the winds by themselves that will also become more more violent, stronger, and cause a lot more damage. So a lot of this has been predicted for a very long time. We see it in the news all the time. We're constantly seeing new record highs in temperature, new storms that become more and more expensive because there are more and more people living on our planet, and they're mostly concentrated in places close to coastlines, for instance. So those are all the many consequences that we have, and the projections are that this is going to become more and more so in the future. And so what can we do about that? It's the first thing that we need to do is we need to reduce emissions very, very quickly, because the more carbon dioxide we pump in the atmosphere, the more difficult it will get. It will both accelerate the climate change that we're seeing, but it will also get more and more difficult to actually remove that carbon dioxide later on, if we can. There are opportunities for doing that already. Carbon capture and storage is mentioned quite often right now. The concern there is that if you capture the carbon dioxide directly where it is produced and you store it away, then that does not really produce an incentive for the industry to avoid the emissions in the first place. But there are other ways of sequestering carbon dioxide directly from the atmosphere. So basically removing what we have put into the atmosphere already, taking that out. And I have a number of colleagues who work in Oman, for instance, who have worked on Iceland. They have looked into opportunities for storing that carbon dioxide in deep aquifers, in basalt-rich environments. So basalt is
actually very, very interesting, if I may interrupt. When you mentioned Oman, because we nominate these game-changing innovators for the Earthshot Prize, Prince William's Earthshot Prize, and 44.01 is one of these solutions. They mineralize captured CO2 in peridotite. Peridotite is a mineral, and they have invented this accelerated process for that. So that's very interesting. In Iceland, I know there is this large direct air capture facility, which Climeworks is building or has built together with the local utility company.
Yeah, and those are actually my colleagues who have been driving this work both in Oman and in Iceland as well. So wow. It's a really exciting piece of work where they in this case they work mostly with in Iceland they mostly work with carbon capture. So they capture the carbon dioxide directly at the exhaust of the power plants, and then pumped it into the deep basalt. So that's that rock that you have directly on Iceland, where you have new seafloor being formed all the time. And it turns out that when you pump carbon dioxide into that rock, it reacts with the water in the rock and it precipitates it as a calcium carbonate. And so that is a very cool way of doing this, because you take the carbon dioxide out of the atmosphere and you precipitate it as a rock. And once it's in the form of a rock, it will be locked into that for hundreds of millions of years, until that rock goes under, gets subducted again, turns back into the rock cycle, and eventually gets molten up and goes back into the atmosphere. So that's a really, really amazing way of doing this, and that's also what is being done in Oman. In Oman, it's actually a natural process that is happening. That's what makes it a very interesting environment to do this kind of research, but also to try and accelerate it. And the problem with that so far is that it still takes a lot of time to do this. But the bigger problem is actually that we don't have enough of these rocks directly exposed at the sea surface, but many of them are actually at the seafloor. And so trying to bring that carbon dioxide down there beneath the seafloor and actually make it react with the seafloor, that is something there. Of which I'm not sure there's much research going on in that direction right now. Right now, the research is mostly going on in places that are more easily accessible. But there are huge quantities of these rocks available, and that's a huge opportunity for putting carbon dioxide into those systems and storing it away for millions of years.
So I think we could probably go on hours and hours and list more and more interesting solutions, because that's that's also something actually we do here at PDIE Group, to look for these solutions and to have a dialogue like today, where we also shed light on the scientific context. What is CO2 and how does it actually really work in the atmosphere, and what is the history of this? This has been a really interesting conversation, and I hope that everybody who will be listening to this conversation will learn something and will be inspired, because it's never too late, and we can all together create a better tomorrow. So I want to say thank you to you, Bärbel, for the tremendous work you are doing, and I hope that probably our paths will cross again, and that maybe you could even become one of the advisors for a program which we are designing now, which is targeting Japanese corporations. So today, thank you very much for being with us, and I will later post this video on our channel. Thank you so much.
Thank you for your interest.